In our theories, there are two kinds of time. There is what is called real time. This is a kind of time that is measured by a clock. The time that we feel passing, the time in which we grow older. Then there is imaginary time. Of course, imaginary time is an idea that science fiction writers, like Arthur, have used in their stories. But imaginary time is also a well-defined mathematical concept. It can be thought of as a direction of time that is at right angles to ordinary, real time, in a certain sense. The universe has a beginning in real time, at the Big Bang. And it may well have an end, if it collapses to a big crunch. But in imaginary time, it has no beginning or end. Rather, imaginary time is closed in on itself, like the surface of the Earth. The surface of the Earth doesn't have any beginning or end. I know, because I have been round the world, and I didn't fall off. Individual particles can travel through imaginary time and arrive back at an earlier real time. But I don't believe that people will ever be able to travel back in time, like in the film, Back to the Future.
So I really like this video. It's got a lot of interesting characters on that stage. We've got Stephen Hawking, Carl Sagan, Arthur C. Clarke, and the Mandelbrot set. So what is imaginary time? Stephen Hawking says that there is real time and imaginary time, and that imaginary time is at right angles to ordinary time. He also said that individual particles can travel backward in imaginary time and arrive back at an earlier real time. Now, I think this is what he said there is actually just sort of a misunderstanding of imaginary numbers and the use of this Cartesian representation of real and imaginary numbers. And I don't think this is a correct interpretation of imaginary time. I think that putting the real and imaginary components onto a Cartesian coordinate system is just a useful mathematical trick and should not be taken literally as they seem to be doing in diagrams such as this. So in Wikipedia, they say that mathematically, imaginary time is real time, which has undergone a Wick rotation so that its coordinates are multiplied by the imaginary unit I. Imaginary time is not imaginary in the sense that it is unreal or made up, any more than to say that irrational numbers defy logic. It is simply expressed in terms of what mathematicians call imaginary numbers. So at least they're saying that, the imaginary label that they're giving to this number is should not be taken literally. And so I think it's good that they say that. But that doesn't really help us understand imaginary time, because now we need to understand what a Wick rotation is. And so here is an example of a Wick rotation. A Wick rotation is a rotation by pi over 2 in the complex plane. So of course pi over 2 is tau over 4. Tau of course is 2 pi. And so we're talking about a quarter turn in the Cartesian coordinate system. So this is a Wick rotation where you have the real axis on the horizontal and the imaginary axis on the vertical. And the Wick rotation is where you take 1 and multiply by I, and you get a 90-degree rotation toward this axis here. And so that is what they mean by a Wick rotation. And again, I don't think this Cartesian representation should be taken too literally. It is basically just a convenient way of mapping what is going on. This is, you can think of this as a map, as a graph. It is not necessarily meant to be taken literally, but it is useful in understanding what is happening when you take something like the number 1 and multiply by I. You get a 90-degree rotation, and then when you multiply by I again, you get another quarter turn, and when you multiply by I again, so this brings you to -1, and then when you do it again, you go to -I, and then when you do it again, you go back to 1. So this clearly shows the cyclic nature of the Wick rotation. So the Wick rotation always brings you back to where you started. And I think this is an important aspect of imaginary time, because imaginary time is cyclic time. Okay, so imaginary time is cyclic. So when you see a graph like this of a wave, like a sine wave, and you see the time component, they often, and this would be real time, when you see real time is usually on the horizontal with an arrow showing the arrow of time, and here you have a wave that is a cyclic wave that is repeating itself over time, okay, or through time. And so so one thing I want you to notice here is that, so the phase of the wave, and I'm doing it in tau, okay, so this is a quarter wave, this is a half wave here, this is 3/4, and this is 1 full wave cycle here, and it goes on and on and on. And what I want you to pay attention here, what I want you to notice is these are called the phases of the wave. So this would be theta. This would be theta. And so I want you to notice that theta is changing, it's going in the same direction. It's increasing in the same direction as time. So time and theta are pointing in the same direction. There's really no difference between time and theta, except that time is measured in seconds, so the unit of time in an experiment. So let's say that this is an experiment. Okay, so the unit of time is in seconds, so let's say we have a 1 hertz signal. Okay, so this is 1 cycle, this is 2 cycles, this is 3 cycles, or alternatively we could say this is 1 second, this is 2 seconds, and this is 3 seconds. So time and the phase of the wave go in the same direction. So at this time here, we've got a quarter of a cycle. We've got a that would be 90 degrees if this was a theta, an angle, or 1/4 tau in radians. Okay, so this is an angle, a phase angle here. This is a phase angle here. So when you get to this point in time, the phase is 1/2 tau, and when you get to this point in time, the phase is 1 tau. So you got 1 complete cycle here, and so on and so on. So time and phase are basically the same thing, only the phase is cyclic. The phase is cyclic, and time is measured in seconds. So this would be 1 second, 2 seconds, 3 seconds if this was a 1 hertz oscillation. So I just want to make a brief statement about my concept of time, which is that time is an emergent property of change. And so if things didn't change, time could not exist. So the measurement of time requires that something is changing. So in this case, we've got a wave that is oscillating. The amplitude is continuously changing. And if we didn't have that, it wouldn't make sense to even have a timeline here. If we had a timeline here with nothing going on, then it would be impossible to apply any meaning to this timeline. So something must be changing. Time is emergent property of change, and if things didn't change, there'd be no point in time. Okay, so I think that's an important point to make right now, because we are talking about time, and it doesn't matter whether we're talking about real time or imaginary time. Something must be changing in order to justify even talking about time in the first place. So now I want to look at this incarnation of Euler's formula. So Robert Distinti, who's an electrical engineer, says that this is the wave function. This is the formalism that electrical engineers use when they're talking about, light, when they're talking about radiation, electromagnetic radiation, in particular radio waves. And so what he says is, if you look in the radar handbook, you're going to find this equation and variations on this equation, and not Maxwell's equations. Okay, and I actually looked, I found a radar handbook, and I looked through it online, page by page, because it wasn't searchable. And I did not find Maxwell's equations, but I found lots and lots of variations on this formula here. So this formula is interesting because it's got the imaginary unit, and it's got 2 pi, which is really tau, and it's got a time component. Okay, so it's got time, and it's got the imaginary unit. And so I want to have a closer look at this to try and get a better understanding of time and imaginary time. So I want to have a closer look at this little part of the formula right here, the 2 pi ft. Okay, and so of course 2 pi, as I stated in the previous video, 2 pi, I am assigning the Greek letter tau for 2 pi just to simplify it, and to just group the 2 and the pi together so that we don't feel tempted to, divide something by 2 by mistake somewhere else. So 2 pi ft is equal to tau ft. Okay, so now what I want to do is I want to do unit analysis on this, because I want to try and figure out what are the units of the 2 pi ft. Okay, so if you take, so we've got tau times f, which is frequency, times time, times t, which is time. So tau is 2 pi, f is for frequency, and time, of course, is the usual measure time, the time of the experiment, the time of the real timeline. So in the previous video, I stated that in modified unit analysis, the units of 2 pi, the units of tau, are radians per cycle, because 2 pi, okay, 2 pi is the full cycle. Okay, 2 pi is the full cycle, and 2 pi is measured in radians, and so the units of tau are in modified unit analysis, where I have a unit, I have the domain, I added a domain, the domain of oscillation, and I have a unit, which I call delta, and so, which is the unit of the cycle, and so tau has units radians per cycle. Also, in modified unit analysis, the frequency has units cycles per second. So instead of just 1 over s, in modified unit analysis, I'm more explicit about how I define this unit. And so, the units of frequency are cycles per second. And so I put cycles back in the cycle term back into the unit analysis. And so I write the units of frequency as cycles per second. And of course, the units of time, the units of measure time, are the time of the experiment. The units of measure time is just second. And of course, the deltas cancel, the seconds cancel, and you end up with the units of 2 pi ft, of tau ft, has the units of radians. So now we can see that tau ft, 2 pi ft in this formula here is the phase angle. So the formula a e to the I 2 pi ft, a e to the I tau ft, is in fact a e to the I times theta, and so this part here, the e to the I times theta, is Euler's formula. This is also Euler's formula, but with an amplitude parameter. So this is basically Euler's formula with an amplitude parameter. And so this kind of clears up what, let's go back to what Robert Distinti wrote. Robert Distinti said that electrical engineers use AE to the J. They use J, electrical engineers use J. J is I, it's the same thing. And so basically AE to the I 2 pi ft is AE to the I times theta. So this is theta. This is a phase angle. This computes to a phase angle. And so there is nothing really special about this equation other than the fact that now we are talking about a wave where the phase of the wave changes over time. So this is the wave function that electrical engineers use. Okay, this is the wave function that electrical engineers use, and they do not use Maxwell's equations in practice. So there's something peculiar about this, but this wave function here is this expression here is what electrical engineers use to solve the problems of electromagnetism. So what has all this got to do with imaginary time? Well, let's go back to Wikipedia and just see what they say. So in mathematics, the imaginary unit I is the square root of -1, such that I squared is defined as -1. We know that now. A number which is a direct multiple of I is known as an imaginary number. In certain physical theories, periods of time, you know how much I love that word, periods of time are multiplied by I in this way. So mathematically, an imaginary time period, and actually interestingly, in this article, I think in Wikipedia, they use tau for this period of time, and so I hope that's not too confusing. I will not be using tau for this unit of time because I use tau for 2 pi. But so this time period may be obtained from real time via the Wick rotation in the complex plane, so which I showed you earlier. But basically what they're saying is you take the real time and you multiply it by the imaginary unit I. So basically what they're saying is to do this, to take I and multiply it by the real unit of time. So I'm going to do it in 2 by 2 matrix format. So in 2 by 2 matrix format, when you take the imaginary unit and multiply it by the real time component, you get time on the backward diagonal of the 2 by 2 matrix, and of course it's got opposite sense. So this is where time sits in the 2 by 2 matrix formalism, assuming that time is in fact imaginary. And as we know, as I've talked about in previous videos, the backward diagonal of a 2 by 2 matrix, of a 2 by 2 complex matrix, is responsible for rotations, but not just rotations. Okay, so it could be responsible for rotations, but it could also be responsible for changes in phases of a wave. And so yes, if you are in Cartesian coordinates and you are using complex numbers, you are going to get rotations about an origin. You're basically going to be drawing a circle, and you're going to be moving by different angles. Of course, if you multiply by I, you go 90 degrees, 180 degrees, 270, 360. But as I showed in the previous video, there's a relationship between the circle and the sine wave. And when you're talking about wave mechanics, we are not talking about Cartesian coordinates. We are talking about changes in phase angle. Okay, so in wave mechanics, we're talking about changes in phase angle when we when we're doing experiment over time. So when you're doing in a circle, when you're doing experiment over time, you are spinning in a circle, and when you are talking about wave mechanics over time, you are continuously changing the phase angle of the wave. Okay, so I think it's very important to distinguish these two situations, because when we're talking about these Wick rotations, we're not always talking about Cartesian rotations from here to here to here and back to here. Okay, in fact, for the most part, when you're talking about electromagnetism, we're not talking about that, because we're talking about waves, and waves have changes in phases over time. Okay, so the time and the phase is changing over time. So time and phase, as I showed earlier, have the same arrow. They have the same arrow. They're going in the same direction. So I think it's really important to distinguish between whether we're going in a circle, you have something spinning, then you're probably talking about this. But if you're talking about wave mechanics, you're talking about something more like this. So it's not always, multiplying by I doesn't always do a counterclockwise rotation in a Cartesian coordinate system. In fact, in wave mechanics, multiplying by I actually does a phase shift. Okay, does a phase shift by a quarter tau, or by 90 degrees. And so instead of a Cartesian rotation of 90 degrees counterclockwise, you're going to get a phase shift. So in this case, we would say cosine is real. Okay, cosine is real, and then sine is imaginary, because sine is shifted 90 degrees, is phase shifted, the phase. So the cosine starts here at 0. Okay, or the cosine has the highest point here at 0, but the sine has the highest point at pi over 2, 90 degrees, or 1/4 tau, or 1/4 of the cycle of their wave. And so in this case, multiplying by I is going to be a 90-degree phase shift. And that is why when you see this formula, you see cosine on the forward diagonal, and you see the sine on the backward diagonal. So cosine is real and sine is imaginary. And in this case, we would say if cosine is real, then sine is imaginary, because it's experiencing a phase shift of 90 degrees, which is not a counterclockwise 90-degree rotation. It is a phase shift on a timeline. So what happens when you use the complex conjugate of time? In other words, if you put negative here and positive here. In other words, when you use Euler's formula, 2x2 matrix version of this formula, what happens when you put a negative here and a positive here? Okay, so let's say I want to rotate by 10 degrees, so I'm going to put 10 degrees in for theta. Okay, what's going to happen when this is positive and this is negative? What happens in my computer simulation is I get 10-degree, every time I click my spin button, I get a 10-degree rotation, 10 degrees, 10 degrees in the counterclockwise fashion. So I get a counterclockwise rotation. And so when I run my software and I make this negative and this positive, what happens is I get 10-degree rotations in the clockwise rotation. Okay, so it's like it's going backwards from where it was going before. It's not going backwards in time, it's going backwards in angle, in phase. And so the complex conjugate does not does not interpret as backwards in time. It interprets as the opposite direction. So it would be, so in this case, instead of starting here and going to here, you'd be starting here and going to here. And so it might look like, because now you're going this way, it might look like you're going backward in time. Okay, it might look like you're going backward in time because you're going down and up and down and up and down and up instead of up and down and up and down and up and down. So it might look like you're going backward in time, but really you're just going in the opposite direction. You're going the opposite direction. So I think that's a big misunderstanding, that the complex conjugate of imaginary time makes you go backward in time. Stephen Hawking even said, oh, sometimes particles can go backward in imaginary time. And I think part of the problem is they have not realized that that time and phase are going in the same direction. Okay, so yeah, you might be going this way in time, but the phases are going backward. But you are not going backward in time. It's impossible to go backward in time. You can only go forward in time, even if the arrow's time is pointing this way. It doesn't mean you're going backward in time, just means the phases of your wave are opposite of what you had when you weren't doing the complex conjugate. So again, when I use this form of Euler's formula, it's easier to imagine on a circle. So let's do the circle again. When I use Euler's formula, it causes me to rotate in the counterclockwise direction. And then when I use the complex conjugate of this, when this is negative and this is positive, it makes my point move in the opposite direction, in a clockwise direction. It is not going backward in time. It's just going in the opposite direction from the non-complex conjugate version of the rotation matrix. And so I think that's all I'm going to do for now. I think hopefully that clears up some of the misconceptions about imaginary time, and maybe gives you a better idea of what is going on with these formulas here. Okay, so that's it. That's all I'm gonna do, and I'm gonna maybe leave you with this one little point that I think is also important. So this formula here is the Euler's formula is actually the equation of a helix wave. It's the equation of a helix wave, and it is the same equation as the equation for a circle. So the equation for a unit circle is x equals cos theta, y equals sine theta. Euler's formula is e to the I times theta is equal to cos theta plus I sine theta. These are really the same equation. All these three are just the same equation. So as soon as you have an x and a y, you are really just talking about 2 by 2 matrix. You're talking about Euler's formula. You're talking about complex numbers. As soon as you have more than just one axis, when you have an x and a y, you need imaginary numbers. And you can imagine that this wave, there's something rotating on a circle, and as this propagates this way, it's going to be creating a helix wave. And when you project the helix wave in the x direction, you get a cosine. You see the cosine, and when you project the helix wave in the y direction, you get a sine wave. Okay, so there's no difference. As soon as you have x and y, we are talking about complex numbers, whether you want to see it or not. So as soon as you have a Cartesian x and a y, you are talking about imaginary numbers. You're talking about complex numbers. You need imaginary numbers. You need both the real and the imaginary in order to write the equation of a circle. So there's really no difference between this and this and this. And that was a huge revelation for me, because you hear people talking about non-imaginary, x and y Cartesian coordinates, and there's really no difference. This is the same equation as this, is the same equation as this, which is this picture right here. Okay, so now for sure I'm going to sign off, and we'll hopefully talk to you soon.